You will present your thesis, study of the interaction between the musician and the instrument application to the playability of the cello. First, I would like to introduce you the members of the jury. So, I have to take the list. Woodhouse Jim, professor at Cambridge University. Wanderley Marcelo, on the video, professor at McGill University, Montréal. Benoît Fabre, professeur à Sorbonne Université, directeur de thèse. Claudia Fritz, chargée de recherche, Sorbonne Université, directeur de recherche, directeur de thèse plutôt. Chauvel Jean-Marc, professeur, Sorbonne Université. Istad Solvi, directeur de recherche à l'Université Aix-Marseille. Ablitzer Frédéric, maître de conférence, Université du Mans. Moulet Paul, luthier à Limoges. And myself, Joël Pouget. Chercheur émérite du CNRS. So you have 45 minutes for your presentations.
Well, we have a member of the jury that does not speak French, and as I'm more comfortable speaking English, I chose to go that way. So today I'm talking about my observations of cellos being evaluated by cellists. This work was carried out at Sorbonne Université with the supervision of Benoît Fabre, Claudia Fritz, and Jean-Marc Jouvel at Lam and Erasmus. We would like to believe that the quality of a musical instrument is something that we could measure objectively, but we have yet to find a satisfactory method of doing so. This is important because understanding the link between the construction of the instrument and its evaluation could help instrument makers more easily meet the demands of their clients. The reason we don't have a solution is that quality is multifaceted, and the importance of each facet depends on the player. Furthermore, an object becomes a musical instrument only when control parameters are applied to it. Since musicians play differently, it is only natural that their evaluations do not agree. In a previous approach to this problem, Bissinger measured physical properties of several violins, but failed to find any correlations with their supposed quality ratings. Fritz and Satis did a similar study, identifying various facets which are evaluated by the musicians, and verified that musicians are self-consistent even though they do not agree with each other. Unfortunately, they also failed to find any correlations between physical properties and player perceptions. A second line of research focuses on the behavior of the instrument in response to a limited set of control parameters. Schelling looked at the set of steady-state gestures and identified upper and lower limits for the bow forces that are consistent with the normal sound of a cello. Gutler identified meaningful control parameters for attacks and used a listening test to find the duration of acceptable attacks transients for the violin. Woodhouse focused on the role of the instrument in relating control parameters to the sounds produced, ultimately leading to the latest models by Mansour. Woodhouse also suggested the movement of the bridge as a physical mechanism which could explain the perception of playability. This hypothesis was tested by Zhang, and she found that there's a good correspondence between the perceived severity of wolf notes and the bridge mobility at that frequency. Askenfeld made some of the first measurements of the three main bowing control parameters in a playing situation, which led to a third line of research in which the control parameters were studied in the context of performance and pedagogy. Schoenerwaltz used a camera-based motion capture system to measure most of the control parameters, and Demicron used a bow force sensor to measure the bow force. Maestre introduced the direct use of the motion capture data to estimate the bow force, and Chudy found that she could distinguish between different players just by looking at their unique ways of using the control parameters. And finally, Chen found that cellists rely on feedback rather than muscle memory to maintain their mental models of the relationships between control parameters and the sounds produced by the instrument. So all these previous studies can be organized according to which parts of the playability feedback loop are varied and what is measured. Our approach to the problem is to make a complete observation of the entire feedback loop by measuring the control parameters, the physical properties of the instrument, and the feedback during an authentic evaluation and performance by a professional musician on two cellos. The comments of the musician help us to interpret the measurements and close the feedback loop. Now, while defining an objective measurement of quality or playability is beyond the scope of this project, we hope to contribute to the discussion by identifying some links between what the musician perceives and the measurable parts of the playability feedback loop, taking into account that these links might depend on other parts of the feedback loop. The specific questions that we will address are the following. What do transient durations tell us about the perception of the instrument? Are musicians sensitive to changes in Schelling's upper and lower bow force limits? And how is the perceived power related to this feedback loop? Next, I'll talk about the experimental design, including the equipment used and the protocol developed for the experiment. And then I will discuss the results as they apply to each of the research questions. And then I'll point to some further observations about the role of adaptation to perception. So we want to understand how musicians evaluate instruments. So the first step was to get a few instruments. Our luthier helped us purchase two cellos and initially set them up to be very similar. The luthier then replaced the sound posts and added a mast to one of the tailpieces. One was made more rigid, reflecting what the luthier's professional clients might prefer, and the other was made more souple, reflecting what his amateur clients might prefer. The idea was that any perceptual differences between the two cellos might be due to these known differences in the setup. We also embedded piezoelectric sensors underneath each string in the bridge. Our luthier made the bridges in an attempt to compensate for the differences in mass and stiffness that results. So why did we decide to make such a drastic change to the bridges? A contact microphone would mix the vibrations of all the strings, potentially masking important information. But by placing sensors underneath each string, we're able to separate their individual contributions. Each sensor uses a pair of piezoelectric elements, which allows us to measure both the horizontal and the vertical components of the force of the vibrating string against the bridge. This allows us to more easily identify anticipatory movements, such as hammer downs, and to study the relationship between the bow inclination and the polarization of the vibrating string, which we wouldn't be able to do otherwise. The design of the sensor is based on the one used by Zhang, and it consists of piezoelectric elements sandwiched between copper tape and plastic supports. We've added holes which allow wires to pass through the sensor so that movement of the wires behind the bridge does not apply stress to the solder points on the front of the bridge, improving their structural stability. All right. So to characterize the physical properties of the instruments, we made measurements of the bridge mobility by tapping the bridge with an impact hammer on the treble side of the bridge or on the top of it, while measuring the acceleration with an accelerometer placed on the base side of the bridge or on the bottom of it. These measurements are used to estimate Schelling's upper and lower force limits. We also measured a radiation transfer function by tapping the bridge with a hammer and measuring the radiated sound pressure at a microphone located 160 centimeters in front of the bridge in the room where the evaluations took place. So during the experiment, we measured the control parameters. There are 6 kinematic control parameters related to the bow. They are the distance along the hair from the frog to the string and its derivative with respect to time, the bow speed. There's also the distance from the bridge to the bow and the inclination angle, which is used to select different strings on the cello. There's the skew angle, which determines whether you're playing orthogonally to the string or you're skew. And finally, the tilt angle, which changes the amount of hair that's in contact with the string. To measure these control parameters, I use a motion capture system, which is based on infrared cameras, which follow the positions of passive markers attached to the bow and to the cello. Cello. The system was chosen because we need a minimally invasive system so that we don't disturb the player while they evaluate our cellos. This system gives us sub-millimeter accuracy, which is necessary if we want to be able to estimate the bow force from the motion capture measurements. The signals from the motion capture system are synchronized with the signals from the bridge piezos using a commercial system. Since the motion capture is taken at a rate of 120 frames per second, we only look for synchronization accuracy at that rate. So here we have a piezo signal for a bow change. And here we see the moment when the string stops being dragged in one direction and begins being dragged in the other direction. The motion capture system indicates that the bow speed is 0 right at this moment, exactly at the same moment when the piezo signal tells us the same thing. So the final control parameter for the bow is the bow force. We cannot directly measure the bow force, so we have to estimate it from the observed deformation of the bow. Dimicron's sensor interfered with playing naturally. It was a sensor that was placed underneath the hair here. So we chose to use a geometric method proposed by Maestre. The motion capture system allows us to measure the endpoints of the string at the bridge and at the nut. And it also allows us to measure the endpoints of the frog line segment, or the bow line segment at the frog and the tip. From these positions, we can calculate the minimum distance between these two line segments. Okay, and we call that minimum distance the total displacement. We can also calculate the distance from the bridge to the bow and the distance from the frog to the string. What we cannot measure directly is the force of the bow, nor can we calculate nor do we know how much of this total displacement is due to the displacement of the hair and how much is due to the displacement of the string. But we can solve for these 3 unknowns using these 3 relationships, being the definition of the total displacement, a model that gives us the force as a function of the string displacement, and an empirical model that gives us the force in terms of the hair displacement. So the force can be calculated from the string displacement given the material properties of the string and its constitutive relations, the geometry of this hair displacement or string displacement triangle shown here, and by considering the equilibrium of the bow force against the tensions in each of the legs of the string. To estimate the force from the hair displacement, we collect calibration data by pressing the bow against the load cell shown here. Note that the bow is deformed by the total force that's applied to it, but the load cell only measures the force along its measurement axis. So we have to make a correction to take into account the inclination angle of the bow. Our calibration procedure consists of placing the bow on the load cell, pressing with increasing force for about 2 seconds, and then slowly releasing the force for about 2 seconds before lifting the bow and repeating the procedure at a new position on the bow. If we look at the data from just one of these press-release cycles, we find that the data is reasonably described by a quadratic function that passes through the origin. If we compare data taken from different positions on the bow, we find that the initial slope and curvature of this function varies. So if we let the coefficients be functions of bow position or functions of the frog to string distance, we find the following model for the force given the hair displacement. This figure shows the position on the bow along the horizontal axis, the hair displacement on the vertical axis, and the estimated force is indicated by the color scale. To make the plot more readable, contour lines have been drawn every half a Newton. Here we say the force depends on the hair depth, but it implicitly depends on the deformation of the stick as well. Since the amount of stick deformation depends on where the force is applied, we expect the accuracy of this model to also depend on where the force is applied. Here we've estimated the error as a function of position on the bow. We see that the middle to upper portion of the bow is well modeled, but that the frog over there and the tip here have larger errors. This is because the hair is fixed at the endpoints, and so any force that's applied is only going to result in a small displacement of the hair. And so any measurement errors in the displacement of the hair result in larger errors in the estimated force. So now that we've discussed the equipment, we can move on to discuss the protocol that we developed for the actual experiment with the musician. We want the musician to behave naturally, so it is important that the experiment mimic natural situations as closely as possible. To do this, we first come up with a plausible context, a reason for the musician to come to our laboratory and evaluate our cellos. Then we come up with an authentic task, one which musicians naturally would have done in the process of evaluating an instrument. We then make sure to justify the sensors and motion capture equipment that's present so that the musician isn't distracted by them and even accepts them as part of the system that she's evaluating. And finally, we state the goal of the observations, making it very clear that we are not using the measurements to make judgments about the musician in any way. Instead, we are using the musician's expert comments to help us interpret the meaning behind the measurements. So the day before the experiment, we give the musician the prompt, the musical excerpts, and our bow with the understanding that the musician will prepare the excerpts in advance and become familiar with our bow. On the day of the experiment, the musician comes in, warms up on her own cello using our bow and setting the tension of the bow. She then takes a break while we calibrate the rigid body model of the bow. Okay? It has to be done at this point because, well, the musician had the bow in her possession before the experiment, and in order to have the best accuracy, the rigid body model should be made after setting the tension of the bow. After the break, the musician comes back into the room, and she's free to evaluate the first cello. After that, she performs the prepared excerpts and then discusses her impressions of the cello. She then takes another break while we take bow calibration data so we can build our bow force estimation model. If at any point the musician had changed the tension on her bow, we would have had to stop the experiment and repeat the bow calibration process at that moment. So after the break, the musician came back in and repeated the process on the second cello. And we ended the experiment by having her compare the two cellos. When musicians evaluate more than one cello, they often do comparisons. And so we're just formalizing that procedure to our benefit because it helps us understand the differences in perception between them. So the musical excerpts that we chose were based off of our observations at Violoncelle en Scène, a instrument making competition where many cellos were evaluated by several cellists. This piece is Gabriel Fauré's Elegy. It's played mostly on the top two strings, and it features the same music played twice in two different ways. It allows the musician to evaluate the expressivity of the instrument on these upper strings and to also evaluate its dynamic range, as one time the music is played forte and the second time it's played pianissimo. Here I've shown the music in tablature, not because we ever see it in cello playing, but because I found it useful when reviewing the data. It helps me quickly identify which string was being played, where the string crossings are, and how far away from the nut the musician might have been playing. So to have an idea of what kind of music our results apply to, we'll listen to this. Okay. The second excerpt was the sonata by Brahms. Every musician that we saw evaluating cellos used this excerpt to understand the power and range of timbres that are available in the lower registers of the instrument. The third you got a thumbs up? All right. So the third excerpt is the prelude to Bach's Fourth Suite. This excerpt has many notes played across all four strings with lots of bow changes. And because of how fast the notes arrive, it allows the musician to evaluate the response of the cello. And because it incorporates all four strings pretty evenly, it helps them to also evaluate the homogeneity of the instrument. So in the interest of keeping the duration of the experiment reasonable, we left ourselves with just these three excerpts. What's missing from these excerpts is playing in the very high registers further down on the neck, which all the musicians had done in the evaluations. And in fact, she also played higher up on the neck whenever she was free to do so. But we didn't look at that data. And also what's missing are bowing techniques that require the bow to bounce and move quickly from string to string. So most of the data that we have here is nearly constant contact with the string as we make bow changes and cross from one to another. The reason that I did not look for pieces that had more technically demanding bowing gestures is because when we saw musicians evaluating cellos at violoncelle en scène, they didn't use those kinds of bow strokes. When the musicians at that same competition who were evaluating bows, they used all kinds of crazy bow strokes, right? And so for that reason, I felt justified in leaving with just these excerpts. So here are the questions that we posed to the musician during the evaluation. No questions were posed during the free evaluation part, but the musician was free to make comments whenever she liked. The important features of these questions are that they are open-ended and non-leading. We didn't want to introduce vocabulary that the musician wasn't going to use herself, and we didn't want her to make comments about things that she hadn't perceived on her own. When we wanted to elicit comments about negative perceptions, we posed the questions in a constructive manner rather than negatively. So what would you like to change rather than what did you dislike? So now that we've talked about the experiment design and the protocol, we can move on to the results and how they were related to the research questions that we asked earlier. The first question was, how are transient durations related to the perception of the instrument? With an eye towards simulation studies in the future, we tried to find a parametric form to simply describe the control parameters during a bow change. To our surprise, we found that just before the musician stops the bow, she actually increases the bow speed by 50 to 100%. Furthermore, this technique all occurs on a time scale that is much shorter than human reaction time. So this particular gesture is something that's planned ahead of time and practiced through repetition. To look at the transients, we take the two piezo signals from the string and find a polarization which maximizes one signal and minimizes the other. Here we see the increased amplitude that goes along with that increased speed right before the bow change. We see a period of constant sticking as the bow changes direction and goes through the zero bow speed. And we see a period of about 7 periods worth of irregular slips, followed by irregular slips that look like Helmholtz motion. Now, what I did was I collected 479 of these bow changes and counted the number of slips, irregular slips that were there by hand. And we see that we get this distribution. We say that there are a large number of perfect attacks, and about 50% of the attacks were acceptable, and that there were many attacks which didn't achieve Helmholtz motion within the observation window. To understand what this has to do with perception, we separated the results according to the cello. And we find that for the rigide cello, there was a much higher probability of having perfect or nearly perfect transients, even though both cellos had about the same probability of having something acceptable. Paradoxically, the rigide cello also had a higher probability of failing to achieve Helmholtz motion at all. To understand what's going on here, we have to break down our results according to the strings on each cello. And what we find is that for string 2 on the rigide cello, there were shorter transients, which explains why there are more nearly perfect transients on the previous page. And strings 1 and 4 had more failed transients, which contributed to the second spike here on the right end on the previous page. So now we ask, how do these transient durations relate to the perception of the string? For that, we look at the musician's comments and the statistically significant differences in the control parameters applied to each string. String 2 on the supercello was perceived as being molle, or soft. The musician compensated for this the effect was that she applied less force to this string in order to avoid touching the adjacent strings. And because she applied less force on average, there was a higher chance that she would have a longer transient duration. String 4 on the supercello was perceived as having a poor timbre. So to compensate for that poor timbre, the musician applied more force to try to get a richer sound. And the secondary effect of applying more force was that on average she had shorter transients on that string. And so that means that for these two strings, which had very different distributions of transient durations, both of them were still perceived negatively. And so we can't make a direct claim that longer observed transients equals a negative perception, nor can we say that shorter observed transients equals a positive perception. Now, we would like to know whether the musician perceives changes in the limits in Schelling's upper and lower limits, and whether it's useful for predicting the perceived playability. The Schelling diagram describes the steady state string motion as a function of bow force and bridge to bow distance for a given note and a given bow speed. It shows that the range of forces that is consistent with the normal sound of a cello has an upper limit and a lower limit. The upper limit depends on the bow speed, and the lower limit depends on bow speed and the frequency-dependent bridge mobility. So from note to note, or from cello to cello, this lower limit changes, which leads us to ask whether the musician perceives these changes. Comparing different gestures, musical contexts, and cellos on the Schelling diagram is difficult because each bow speed, string frequency, string bridge mobility requires a new set of upper and lower limits. Note that the Schelling diagram has logarithmic scales, and that they are always normalized against some reference. Here the force is normalized against an arbitrary constant, such as 1 Newton, and the bridge to bow distance is normalized against the string length. So what I've done is to normalize the bow force against the changing upper limit. And this allows me to compare gestures at different bow speeds. Then I normalize the bridge to bow distance against the distance between the bridge and the point where the two limits intersect. And this allows me to put all the data I collected over various bow speeds on different notes, different strings, and different cellos, all on the same diagram. So what do we see? When we place every frame of data from 1,300 notes, we see that, yes, the musician played near the limits and sometimes went beyond them. But it didn't happen very often. And because of the ambiguity in this diagram, we are not sure whether the musician's control parameters passed the limits, or whether the limits came down and passed the musician's control parameters. Here I have a representative sample of the data with force plotted as a function of time in red. The upper limit is in black and the lower limit is in brown. The background colors correspond to the string that's being played. Looking at the top graph, we see that the upper limit in black is usually something like 20, 40, or even 60 newtons. But the cellist can only apply about 10 newtons before the bow hair touches the stick. So Schelling's upper limit is usually much greater than what the bow deformation allows. The exception is during a bow change, when the bow speed is nearly 0. This makes the upper limit go to 0, and any force that the musician were to apply would have necessarily been above the maximum limit. The bottom graph makes it easier to see that the musician went below the limit only when lifting the bow off of the string, and that for normal bow speeds, the Schelling's lower limit is well below the minimum force that the musician felt like she wanted to play. So why didn't the musician use a lower bow force? I'm not sure, but I think maybe there's a certain amount of minimum bow force necessary to have acceptable transients in general. So what happens if we insist on, oh, before that, I have some thumbnails. Yeah, so some thumb rules are that the upper limit, it tends to be greater than 20 newtons, and lower limit for typical bow speeds tends to be less than 0.2 newtons, whereas the musician plays with forces a bit above 0.2 and well below 20. So what happens if we insist on using the Schelling diagram to compare instruments? We get results like these. We designed our experiment to have comparable data sets on each cello. Since the same musical contexts were played, the musician used similar control parameters, which we see as similar cloud shapes. We cannot see the slight differences because the diagram is on a log scale, which only demonstrates order of magnitude sorts of changes. However, if the bridge mobilities are different, significantly different, as in what we see with the wolf note, then we see shifts in the clouds. And here we see that the rigid cello in blue actually has notes that are close to Schelling's limit at the wolf note. And so the wolf note is likely to be perceived more severely on this cello. Now, suppose that a cellist says that one string is more powerful or louder than another. We could check the microphone, but without knowing her control parameters, we wouldn't know how to interpret the results. Now, we already have the idea that power or loudness is related to the radiation transfer function, but then we have to ask which radiation transfer function, the one measured with a horizontal excitation or the one with a vertical excitation. Well, the obvious answer seems to be the excitation along the axis of string vibrations, which should be the same as the bow inclination angle. But when we look at the bow inclination angles, we find that each string has a range of inclination angles. And furthermore, that the bow inclination angles do not equal the polarization of the vibrating strings for each note. There is a range of bridge force polarizations that could be applied to the bridge mobility or to the radiation transfer functions. And so for a given note, we wouldn't know which one to use. But global impressions are made after playing many, many notes. And in that case, the musician is likely to have sampled the entire range of polarizations that go into the function. So if we want to find some link with perception, we should look at the entire range. Here we have plotted the range of radiation transfer functions over all string polarizations for each cello. Note that since the radiation transfer functions are complex valued, the maximum amplitudes may be greater than either of the two measured amplitudes. And then likewise, the minimum may be less than either of them. We've also measured the ratio of the root mean square amplitude of the microphone signal to the root mean square amplitude of the piezo signals for each note. And we plotted them as points on top of the radiation transfer functions. The musician commented that the lowest string, so the lowest string here, was perceived I lost my place. The musician commented that the lowest string was more powerful for the supercello than for the rigid cello. And we see that the soup ratios in yellow tend to be higher than the rigid microphone to piezo ratios in blue. If we look at the radiation transfer functions for each note, we find that the maximum for the fundamental of the soup cello, here in red, tends to be greater at the fundamental, or if it's equal to that of the rigid cello, we find that the first harmonic on the soup cello is greater. The one exception is the last note. They're just above 92 hertz. There, the transfer functions are equal. But if we look at the first harmonic, we find that the rigid cello has a higher radiation transfer function. And that's consistent with the location of the piezo ratios that we found for that note. So it'd be interesting to follow this up with a focused perceptual study using more carefully taken measurements. So now I'd like to point out how important the role of the control parameters are in the perception of an instrument by giving an example of how the perception changed as the musician adapted to her control parameters to the instrument. Here are several attempts to play a single long note in the Brahms excerpt. On the first attempt, the musician did not get the desired range of timbres, and she initially diagnosed this as a problem with the sound of the cello. In her second attempt, she used a little more force, but had problems touching the adjacent strings. So in the third attempt, she used a little less force and didn't get a good result. And in the fourth attempt, she tried moving the bow higher, away from the bridge, and trying to get different sounds using her bow speed. At this point, the musician realized that there was a problem with the string she was playing on. It was a little bit low compared to the adjacent strings. And with that knowledge in hand, she then placed the bow closer to the bridge, where she was able to apply a much greater force at the very beginning. And therefore, throughout the note, she had a much larger change in the force and a change in the timbres available. And so an initially diagnosed problem with sound was eventually perceived as a problem with geometry. Here are the first two notes of a Bach excerpt. So why am I showing this? We originally had the idea that we might be able to observe this kind of adaptation without the musician's comments. And in this case, there are some quite large changes in the control parameters, but we weren't always so lucky. Here, the first two notes of the Bach excerpt, the musician complained that there was a lot of richness between the first two notes, which we can see in the spectral centroid. By adapting her control parameters, she was able to find a successful set of control parameters, which we see by the equality of the spectral centroids at the end. And while there are some rather large changes between the different attempts in the force, those large changes are still on the same order of magnitude as the forces, as the variation of the force within a single attempt. So it's not clear to me that any statistical method of identifying these changes as being meaningful rather than natural variations would be successful. So as we draw conclusions from the data we just looked at, we need to keep in mind that the results are specific to the perceptions and control parameters supplied by one musician on these two cellos with the three excerpts that we saw before. Our overall goal was to find links between the musician's perceptions and the measurable parts of the feedback loop. To approach the goal, we asked three more specific questions. The first question was, what do transient durations tell us about the perception of the instrument? And the answer is not much. Transient durations have more to do with the control parameters that the musician chooses to apply to the string than to whether or not she perceived the string as being in a positive way or in a negative way. For example, when we saw that strings 2 and 4 on the soup cello had different string transient durations, but were both perceived negatively. The second question was whether musicians are sensitive to changes in Schelling's upper and lower bow force limits. And here the answer is clearly no. The musician's upper bow force limit is posed by the deformation of the bow, and the smallest bow force used by the musician is likely an order of magnitude less. The smallest bow force used by the musician is likely an order of magnitude greater than the limit. And maybe this is related to transient durations. So Schelling's limits are not likely to be perceived by the player, except in the case of the wolf note, and so will likely not play a role in the evaluation of the instrument. The third question we posed was how the perceived power is related to the feedback loop. And we found that the perceived power of an instrument might be an intrinsic property of the instrument, not related or not depending on the control parameters applied by the musician. And we suggest a way to relate this perceived power to the radiation transfer function measurements by looking at by considering the range of polarizations that we apply to each measurement. Now, to respond to our overall question, we have the following chain of logic. Playing the cello involves continually updating mental models. This is what we learned from Chen, 2008. And that applying the model update algorithm to different cellos may result in different final values of the control parameters. And this may be unconscious because for the player, they followed their method of playing the cello, which is to update their models continuously. They then make quantitative measurements of the control parameters. This is what I learned from interviews during violoncelle en scène. Now, applying unconsciously adapted control parameters results in a perception that may not accurately describe the instrument. Earlier, problems with the geometry were initially mistaken for problems with the timbre of the instrument. But by overcoming these perceived problems through conscious adaptation, a more stable perception may be found. So we saw that in the same example. So finally, we conclude that previous research attempts to connect playability and sound to vibroacoustical measurements. But playability and sound are interconnected facets. Playability is highly influenced by the geometry, both absolutely and relative to other cellos. And sound is highly influenced by the control parameters that the musician chooses to apply to the instrument. Thus, neither playability nor sound is necessarily something that we can extract just from tapping the instrument with a hammer. Thank you.
Okay, thank you, Timothy.